Alright, in part 2 here, let's talk about number 7. DBC and ADB are complementary. We don't really have a marking for that. I'm just going to put these little dots here. I know that they are complementary. ADC is congruent. ADC is congruent to ABE. Interesting. And this thing's a bisector, so that little part is congruent to that little part. Well, that little part was complementary to this. These are the same. I've got a complementary and I've got a equal situation here. Let's call this one x. They're both the same. This whole thing then is 2x. Great. And I was congruent to this one out here, so that's also 2x. I can say this is 2x too. And now I just found out that x and 2x are complementary. That's one way to do that. There's other ways to do this. I could have called this 90 minus x and gone, oh look, 90 minus x equals 2x. Any way I do that, I'm going to figure out that x is 30. I guess you don't have to do that with algebra, but it makes it a lot easier. So this part's 30, this part's 30. The whole thing, of course, is 60. If x is 30, these are 6. Sorry, these are 60. I said 60. I wrote 30. That makes these 120. And that part's 60. In this little triangle I have a 60 and a 30, so that means that has to be 90. In this big triangle I have a 90 and a 60, so that makes this part 30. Or I could look in ABD, I'd find it's also 30. Okay, great. Number 8. Oh yeah, this is a long one. Regular pentagon. Alright, so in a regular pentagon, I'm asked first to find the measure of any one of these angles. On a regular pentagon, I think the easiest way to do this is do the exterior and go, oh yeah, this one out here is, well, 360 because the exterior is always add to 360, divided by 5 because there's 5 of them and they're all the same. So that's 72. So each one of these ones in here is 108, and that's all of them. I think I'm going to need these later, so I'm going to go ahead and put these in. All the measures of the interior angles of this whole thing is also 108. Why is 5 equal to 6? Well, if these are parallel, it tells me at the beginning those are parallel. This is the fact that parallel lines tells me that AIA angles are congruent. Great. 4 plus 6, oh, I just marked that. That's 108. That's one of the angles of the pentagon. Find 3 and justify. Well, 3 here is part of this same side interior situation with CD and BA. It's same side interior with this 108 I just found down here. So this has to be 72 because parallel lines imply that the same side interior angles are supplementary. So this is 72. Great. So hey, if that's 72, this is 108 I'm talking about here, the next question. And you can also say that's 108 because it's corresponding with 4 and 6. And this angle here with the D in it here, CDG, that's corresponding with the 108 down here. So in this pentagon I've just been asked about, I've just shown that all of those are 108, basically corresponding with the original angles. The original angles in the, I'm going to say angle B. By angle B I mean this whole thing here. That's angle B. Corresponding with the angles of the original regular pentagon. They're corresponding, so they have to be congruent to the originals. Okay, I can't find everything. I can't find 4, 6, 5, and 2. That's kind of annoying. But if I knew that DB was a bisector, if I knew these two, you know what, let me change color because I think I'm going to undo this in a minute. If I knew this was an angle bisector, first of all, I know this whole thing, 5 plus 2, has to be 72. Just like that, it has to be 72. That makes each one of these 36. And remember, 5 was AIA with this one, so this is 36. And this sum is 108 from that angle B thing I was talking about before. So that has to be 72. Can I find all the angles? Yes. So that's the stuff in blue. I'm just going to say that's the blue stuff. Now forget about the blue stuff now. We're going to go purple for G. Blue for F. For G, you got to forget about blue stuff. I'm going to leave it there because I want to print this sort of later. And you can see what goes with that. If you knew 2, could you find things like CDF? CDF is crazy. CDF goes from here to here. I kind of want that to be a different color. CDF is like this thing. How come that's not green? Make it green. Or make it purple. One of the two. There we go. This angle. Can you find this if you knew angle 2? Well, if I knew angle 2, I could find everything here that was in blue before. That's not bad. But, you know, can I find this thing? This thing's crazy. I don't actually think that I can. I agonized over this for a long time. I know that these two have to 108. I was looking at things like, well, this quadrilateral FDCE. I can't find it. If I knew something about this angle here from, you know, EFD, then of course maybe I could do it. But with trigonometry tricks, I'm pretty sure I could find it. But I don't want you guys to start thinking about trigonometry tricks yet. So if I actually made up some labels for lengths of sides and things, maybe, but with just pure angle discussion, I don't think I can. I want to say no. I could be wrong about that. This seems way harder than a test question. It's fun to think about, but I don't think it's possible. What's 4 minus 2? Well, what intrigues me about this problem, I'm going to go back to blue, because for a second we had this 36, 36, 72, 36. If 4 minus 2 is supposed to be any kind of constant answer, then it should be the same as this one example that I've got filled in here. I want to say that if that's supposed to be constant, then it should be fine that that's always going to turn out to be 36. Again, a little bit beyond the scope of this test, but fun to think about. Okay, number 9. AB, let's go back to red, my general answer here, or general thing. Answer color, those are parallel and those are parallel. If ACD, which is this one, is 132, so I like to measure, like write that in this way, and BCD is 67. Well, hold on a second, let's just do this now. If that's 67, the whole thing's 132, then I know what this part is. It's kind of silly. It would be 65, is that right? No, 75? No, 65 is right in the first place. Yeah, 65 and 67 is what they're doing. Yeah. Find E and justify in two very different ways. Well, I just used sort of angle subtraction here, like the fact that these two were stuck together, found out that the 65 was here. I know that 65 is corresponding with E. So I could say corresponding with angle ACB. That's one way to do it. Another way to do it is with this, you know, with the transversals and the with the parallels and everything I have here. I could also talk about this angle in here, DCE. I guess it's the only double rainbow angle I have. Is part of a triangle with this angle over here. I could make a triangle CDE. I know that the 67 is AIA over here. 67 here, and this double rainbow here is what do I say? Linear pair with the 132. That makes it, is it 48? So I could go triangle sum. And triangle sum 67, 48. I want to say, yeah, that's going to have to be 65 also. Is that true? 160 and 20, yeah. With angle DCE and angle CDE. Yeah, very different. One is about just parallels, one was about an actual triangle. If DE is perpendicular to DB, okay, do I have to pretend none of this stuff is true anymore? I bet I do have to pretend that's it. Well, let's see if I have to erase that or not. DE is perpendicular to DB. Okay, so let's draw into DB here. Let's say that was perpendicular, like this. ABD, angle ABD would be the same size, could ABD be the same size as any regular polygon? Well, let's assume that we mean all this stuff is going to stay here then. If that's 90, that makes this, have to add 90 with that, so that's 23. Can I figure out what this is? Oh yeah, those are parallel. So if this is 23 here, this is 23 out here. Oh yeah, look at that. This is 23, so this is just simply supplemental to the 23. So this thing in here is probably 157, right? Actually, I think this 23 is a little more helpful when we're talking about if that can be if this can be a regular polygon angle. If this is a regular polygon angle, here's the exterior angle of a regular polygon. The regular polygon would have to have this many sides. Well, this isn't an integer. This is some crazy number with a decimal on it or something. This is about 15 point. That's approximately equal to 15.65, which is not an integer. So we're going to say no. If not, say how many sides a regular polygon has with the angle closest to this. Well, 15.65 doesn't work. If it had 15 sides, so it's between 15 and 16. A 15-sided regular polygon would have an exterior angle of 360 divided by 15, which is 24 on the outside. 16 would be 360 divided by 16, which is 22.5. Which one are we closer to? With 23, I guess we're actually closer to the 16. We're only half a degree off. By the way, this was 360 divided by 15. This is 360 divided by 16. So we're actually a little bit closer on the 16 gone. All right, I have a little bit of time left. 4.5 minutes. Oh yeah, this is where they get easy. Oh, sorry, this isn't going to fit in the window. I'll just have to scroll. Okay, so with these here and this right angle marked, I think it's real easy just to start putting stuff in. Here's a 90 degrees, 30 degrees. Of course, these have to be complementary from that one theorem. This is 90 on this side. Again, I got complementary over here. While I'm at it, let's just go ahead and talk about this whole thing. That's got to be 105. And in fact, those are the things that I'm asked about. A, C, B, D, and A, B, C. Okay, CBD is what kind of triangle? And there's two names here. This implies we're talking about a side name and an angle name. The angle name is not bad. CBD, this is one over here. It's got a right triangle in it. What I would not expect you to know on this test is the side name. It turns out it's scalene. I think everyone probably would have guessed that it was scalene, but we haven't really talked about why it has to be scalene in a question like this. E, can I fit all this in here? Yeah, sort of. E is ABC. ABC is the big one. Of course, the biggest angle here is obtuse, so it's the big angle at B is in that triangle because it's 105. Again, it happens to be scalene, but I wouldn't ask you scalene based solely on angles, which is what this is asking you to do. So all these, since you don't have sides here, I think that's kind of a bad question. But to ask you to assume what you know about sides based on angles, but it's not. I mean, it's again, I don't think anyone would have missed it. It just doesn't quite belong in this question. If I was going to ask you this, I'd probably put like, okay, this side is 10 and this side is 15, and this, I'd give you some lengths because that's all we talked about for how to get these. ABD is got a right angle also at angle D. This one might be even easier to see, even though it's the weird one. This one turns out to be isosceles. Okay, I got to move this back up just so I can turn the page. All right. Do we have enough time for another bit here? I bet we do. Let's see if I can just get a couple more in here before time runs out. Given the following diagram, determine the values of blah, 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 blah. Well, the easiest one here probably is this one. We have a linear pair here with x. Then I got a triangle here to find y. That's got to be 180. I think a tempting thing to say, oh, well, z and y, those are AIA. Well, they're only AIA if these are parallel. They're not parallel. So I got to do it with this triangle here. 65s are vertical, so I think z turns out to have to be 25. Decagon has 10. Some measure for exterior angles of a, I don't even care what this is. It's always 360. Interior angle is, well, if it's a hexagon, you're getting used to drawing these this way. Each one of these is 60 because it's 1/6 of this total. So the part on the inside here has to be 120. You could do that the long way, or you could do it that way. You'll get 120. 14, measure of each interior angle of a regular polygon is 170. The exteriors are 10. And then how many sides would have? If each one of these is 10, and they have to add up to 360 all the way around, that means there would have to be 36 of them to equal the total. Okay, I think that's a good place to stop for now. I will see you in part 3.